the subject for the next 2 lectures I'm giving. So several people have asked me, and it's a pretty common kind of question. We've been using Coq to, in some sense, verify functional programs written in Coq. Though in the last few lectures we saw formalizing the semantics of other languages, like different functional languages, not just Coq, not just the functional language built into Coq. But you might want to, say, verify your big old grungy C program, in which case, first, you have my condolences. Second, what I'll show today will go some way towards making that possible. And I want to try to show how we can, without giving up the very strong formal guarantees of a system like Coq, we can provide a pretty effective, high productivity environment for verifying programs in a language that's completely different from anything built into Coq. And sort of the standard to compare against is this picture that's embodied in a number of tools that exist today. You might have heard about tools like Boogie and Daphne, which are in the sort of classic program verification mold, where you have your program, and you'd like to prove that this program meets some specification, which is formalized logically. And to establish that, you're not going to write out a manual proof like what is standard in Coq, but instead you're going to annotate your program with enough information to give away sort of the hard parts of that proof. And a classic example of that is Loop Invariants. Don't worry if you don't remember what Loop Invariants are, or you've never seen them, because I'll be introducing them again a little later. But so you have these ingredients, you feed them into a program verifier, which is it's some program that embodies a particular verification methodology. And how this tends to work is that this program translates all these ingredients conceptually into one big formula of usually first-order logic, such that if this formula is true, then your program meets its spec. And if it's false, well, that might just be an incompleteness in the methodology. But as long as the SMT solver says, yes, this is a true formula, then you can push this reasoning conceptually all the way back and deduce that this program really meets its specification. Now, an important thing about this picture is which boxes are trusted, in the sense that if there's a mistake in one of them, we could accidentally accept an incorrect program. So I'll draw a boundary for that. I think the boundary roughly lies here, where in this traditional picture we have basically all the parts of this picture except for the program and the annotations are trusted. A bug in the program verifier can completely scuttle all the guarantees you'd like to get. If the SMT solver accidentally says, yes, every formula is true, then you'll be in some trouble. And if you got the specification wrong, then you might prove a theorem, but it's not the theorem you wanted to prove, so you have to make sure you got the spec right. But your program itself, and also the annotations you write on it, are being checked by these tools, and if the tools are correct, then you won't be able to trick them by putting incorrect values in for either of these 2 boxes. But this is still a pretty big, trusted part of the picture. An SMT solver alone is a pretty significant piece of engineering, and it's easy to introduce bugs there. So I'm going to draw into this picture also the Coq proof checker, which we've been implicitly relying on all along. And I'm perfectly willing to put this inside of the trusted perimeter. Turns out that the core Coq proof checker is basically just a type checker for a dependently typed lambda calculus, and it is small relative to either of these things. And it could even be small relative to the program you're verifying, depending on what your application is. So given that we've introduced the proof checker into this picture, does anyone have any suggestions for how we could shrink the amount of code that we're trusting? Some of these suggestions are already implemented in various tools, though they're not as commonly used as the picture I started out with.
Do an operational semantic to better Hora Logic.
So I didn't introduce, though I wrote the words Hora Logic, I didn't explain what it is yet. But let's say instead, one approach is to prove that this box is correct in Coq. That is something we could do. There's a sort of lighter weight approach we could use that's probably less work that would still shrink the trusted code base. Yeah?
So your program verifier can generate the proofs that they're doing the right thing well?
Yeah, so imagine we could do it this way. I'm going to move the program verifier outside of the trusted section and have it generate proofs that go into the Coq proof checker. So every time it runs and analyzes a program, if it decides program is okay, then it outputs a Coq proof, which we can check independently. Now we don't need to trust the program verifier anymore. Are there any other opportunities for bringing boxes outside of the trusted base here? Yeah? So we definitely need some way of coming up with the theorem statement that we're trying to prove. And that you could consider to be part of the program verifier, which we would need to trust. But the argument about why that theorem is true, we shouldn't need to trust that as long as a proof is produced on every run of the tool. Does that make sense?
I guess I'm not seeing how you know that proof corresponds to the program. Isn't just a proof 1 equals 2 or some sort of proof.
Because you're running the Coq proof checker, which takes as input not just a proof, but also a theorem statement. Any other ideas for how to shrink the trusted code base here? Yeah. We could verify the SMT solver, but there's a simpler version of that, which is let's take the yes answers and have those come along with proofs that the SMT solver is generating. And then given that, we can, how am I going to draw this? This is getting geometrically difficult. I'll just make 2 blobs. The things that are trusted are now the spec and the proof checker. So that's one way to do this. And the advantages of thinking of things this way are that you have sort of one core system that is your idea of truth and provability and convincing arguments, and then you can build a number of libraries and associated tools that improve the productivity of the users of your platform, but which don't need to be trusted. And I see this situation sort of like if in the world of programming, for every new program, you have to implement a new domain-specific language, where there are opportunities to introduce bugs in the implementation of every new domain-specific language. And I think this would really be unfortunate for programmers to have to do that for every new program. Sort of building specialized program verifiers, like the things that sit here and here, I see in a similar way. All of these systems should somehow be connecting to a common foundation so that we don't need to trust them, or so that we can think of them more like libraries instead of entirely new tools. So I will be showing how we can replicate this picture entirely inside of Coq and still realizing a similar programmer experience to using standalone tools. And I'm not going to necessarily verify a program verifier, but we will do this in a way so that every program verification does output a proof, and the equivalent of the logical questions that are being asked to the SMT solver, every yes answer is generating a proof. So we don't need to trust any of this. We're just going to be trusting, similarly to this picture, the specification and the Coq proof checker. Any questions about that general proposition before I start going into the details? Yeah?
Are there currently any SMT solvers that do plug into Coq?
There are. I think they might all qualify as experimental and partially bit-rotted at this point, but it's pretty, in my experience, it's pretty straightforward to do if you make proof generation a goal from the start of your SMT solver project, which hasn't been true for too many so far. But I don't think there are many scientific challenges left. All right, so the first step to doing this is to be very precise about what correctness of a program means. So I'm going to show you first, we'll take a brief detour into operational semantics for a simple imperative language, sort of like C. And here's the syntax of that language in this Coq code. And for this lecture and the next one, I'm going to skip over larger parts of the code and focus on explaining things at the whiteboard level. And if you want to go back and read some of the Coq tactic code that's supporting the proofs that will come at the end, that's a useful thing to do offline. But I'll mostly flash up some code and then explain it most in informal whiteboard notation. And so here's our language. At the top is a language of expressions, which contains all the usual kinds of things, plus an operation to read from a memory location. we'll be able to use that to do pointer kind of stuff. And then we can give a semantics to the expression language in a very standard way. We've seen notation like this in Moll's lectures. It's really, the syntax might be unfamiliar, but it's basically, this is a way of defining a 3-argument function. Here's the first argument, here's the second argument, here's the third argument. This first argument is an expression. The second one is, this is a sigma. It's a variable environment that maps each local variable to its value. The values will just be natural numbers here. And M is a memory, which maps numbers to numbers. It tells you for each memory address what's stored at that address. So the meaning of a number constant is just that number. And the meaning of a variable is just the result of looking up that variable in the variable environment that we've taken as an argument. And the meaning, I'll write a memory read operation like this, sort of treating the memory as an array and subscripting into it. The meaning of that is just what we get by looking up. The memory is a function from addresses to values, so let's just call that function on the right address, which we get by evaluating the sub-expression that's associated with this memory read. And finally, if we have an addition expression, this is just equal to the sum of the values of the two sub-expressions. Yeah?
What's the first word on the third line? Then the up arrow?
It's an open bracket.
Oh, I see.
Yeah. It's meant to suggest an array dereference. All right. Any questions about that? This is what we might call a simple denotational semantics, to use terms that we have mostly avoided for the summer school, but it's really just a recursive function that translates from one type into another, where we sort of understand the second one better. All right. So the next ingredient is the semantics of the commands in this language. There's also a language of Boolean expressions where I've just included equality tests and less than tests, but that's similar enough to the other case that I won't go into the details. But we have a language of commands with a skip command, which does nothing, local variable assignment, memory write, which is like assigning to the result of dereferencing a pointer in C. Sequencing to run one command after another. You can basically read this as semicolon. We have an if statement and a while loop. And for now, we'll ignore this invariant argument of the while loop. Pretend that isn't there. And the while loop just takes as argument a Boolean expression and a command. So we have to give a semantics to this kind of program. And it's going to be a big step operational semantics. The form of the judgment is a little different from the ones we've seen before, because now we have this state that gets mutated in the course of running a program. So the judgment is going to look like this. As an input, we have a triple of a command, a variable assignment, and a memory. And then in a big step, this runs to a new variable assignment and a new memory. So the meaning is, when we start out with this assignment and this memory, this command runs and terminates, and the side effects it causes produce this new variable assignment and this new memory. These could be the same as the original ones if this command actually has no side effects, or if it somehow undoes any changes that it makes in the meantime. So I'll just give a few representative rules of the operational semantics. The simplest one is skip, so let's take advantage of that simplicity and say that if you run skip in any state, any guesses what the output is of running skip? It's the same state we started with. Doesn't change any of the variable values, doesn't change the memory. All right. And then if we have a variable assignment, and by the way, I'm going to use more standard syntax for these commands, not directly following the Cox syntax over there. Let's say we have an assignment into a variable. This corresponds to the assign constructor up there that takes a string, that's the variable, and an expression, that's this one. What do we think is the result of evaluating this? I'm hearing some rumblings.
Sigma mapping X E.
Yeah, so I'll just write that as, to be consistent. Let's see what I'm writing here. Sigma, take the sigma we started with and update it with a mapping of X to not just E literally, but the result of evaluating E in the current state. And then the memory is the same as before. All right. And another important one is the sequencing, or the semicolon. So to do this one, if command number 1 in this state runs to this new state, and then let's take command number 2 and pick up running where we left off with the new state, and this terminates in some further state, then that means if we run command 1 followed by command 2, that has the same effect as running both of the commands individually. So there's sort of a lot of verbiage here, but if you think it through, it follows naturally as the sort of the only way to make sense of sequencing. And the last representative rules that I'll show are dealing with the while loop. Here are things, we're actually going to have two different rules here. Let's ask what happens when we run a while loop with the test expression B and the body C. Here's the state. So if we know that the test expression in the current state evaluates to false, then what should we conclude in this rule? Yeah, then this while loop has no effect if the test expression is already false. So we get back to where we started, and I think I should switch over here at this point to avoid going too far off the bottom there. There's one other rule that we use for the case where the test expression is true. What do we want to do? We'll need some additional premises. If the test expression is true, if we need to make one loop iteration, how could we phrase this formally to express the conditions under which this loop is going to terminate in some state?
You can expand it out to a sequence and a while.
That's a pretty economical way to do this. So let me write it that way, especially to save space on the board. I'll say, if the test expression is true, then what that means is run the body and then run the loop afterwards. So this is telling us what happens when we run this loop in this state we get here. All right, so I omitted some of the other statement forms which are similar to these, but I hope this gives a basic idea for how we can be completely formal about the behavior of programs like this. And maybe you might be convinced that we can lift this to, say, semantics of the C programming language. You might believe me if I say it's a little more complicated, but this is the basic idea. Any questions about this? Do you believe that we've defined the meanings of these programs unambiguously? Yeah? I think you're referring to denotational semantics, which is a different approach that I'm not planning to cover today. It's pretty disfavored in the community today. Operational semantics tends to be easier for people to understand and apply. Yeah?
This is static analysis, right? So how do we know whether B is true or false?
This is, think of this as an interpreter for the programming language that we'll use to state some theorems. This isn't the final machinery we use to verify individual programs, though. Yeah.
So if you had like again, I'm wondering why you didn't put a down arrow false for the Boolean. I mean, what if that is like an expression?
It is an expression, but we've defined expressions so that they obviously terminate, and you can write a simple recursive program that computes them. It's not the case for the command language because you can write while false skip, and you have a non-terminating program, so you need to get a little more fancy to capture the meaning.
Okay, so I got. So can you tell me one more time why you didn't use a down arrow for that?
Types of B and C are different.
Okay, so
We-
down
we-
arrow is only for the command.
Yeah. Uh-huh.
Can we book termination using Hora Logic?
We can. I wasn't planning to cover that today, but yeah, that's a venerable topic that you can look up in a variety of sources, including, I think, some by Hora himself, or maybe Dijkstra. All right, so some of these questions are leading us in a good direction. How are we actually going to prove the correctness of programs? It's not very effective to reason directly about this semantics. So that's where the title that I wrote for this lecture comes into the picture. Hora Logic. And let's see, any votes about a better one of these two boards to erase at this point? I see, I'm seeing contradictory pointing. And I'm concluding false. All right, we can do anything. Yeah, I'm going to go, so I wrote this least recently, so I'll follow that eviction policy. I'll leave the while rule on there for now, though. So the approach that we're going to use to actually verify these programs is something called Hora Logic, which is based on one simple convention for stating theorems, where we write assertions or propositions like this one. So C is the command we're verifying. And on the left here, we have the precondition, and on the right, we have the postcondition. And think of P and Q as arbitrary propositions that are allowed to mention the values of the local variables and the memory that C could manipulate. And what this means is, let's say we have some initial state, and we are going to run C in that state and get to a new state. What does it mean to run C? It means that we take this operational semantics and we say, starting with C, sigma, and M, we run that and we get to sigma prime, M prime. So this is, again, by the definition of the semantics, we're only considering terminating executions here. And what we're going to do, the meaning of the precondition is that we're going to assume that the predicate P holds of the initial state. And then what the Hora triple says is our obligation is to prove for any way that this run could develop, we need to prove that the postcondition holds of the new state. So it's a pretty simple definition, even written out completely formally, which I won't do here. It's a nice, simple definition, and even simpler when you draw it as a picture, as it often turns out. And I can give some examples of rules we can use to deduce facts like this. And a program verification will basically just reduce to applying these rules over and over again until all the program syntax has disappeared, and we wind up with formulas that are sort of like what is traditionally passed to an SMT solver by standalone program verifiers. Before I start showing some rules, any questions about how this is actually defined in detail? Does this make sense as a way to specify how a program should work? Yeah. I didn't mean we're proving that programs always terminate or even assuming it. I mean that the correctness obligation only requires us to prove a property for terminating executions. If the program runs forever, then it satisfies any spec. So this is called partial correctness for that reason. There's another notion called total correctness, which additionally requires we prove termination. Partial correctness is much more commonly used today. Termination is just a whole other layer of bureaucracy to deal with, and most people tend to skip it. Also, some programs are expected to run forever, so there's that complication too. Okay. I'll just show you quickly the way that the Hora triple is defined in Coq. I just paged through the equivalent of the operational semantics I wrote. Here's the Hora triple. P is an invariant, which is basically a predicate over machine states. C is a command, Q is another invariant. We say for every state where P holds, if we exec from that state to another state, then Q holds in that new state. So let's run to this point. And then I define a whole bunch of syntax stuff here. I'm not going to explain Coq's facilities for extensible syntax, but it's pretty cool stuff. You can use it to basically, as I'm going to do here, embed a C-like language inside of Coq and write natural syntax to do proofs of those programs. And it might be worth looking at some of the details of this afterwards, but for now, take my word for it. This does what I just said it does. And here's a nice syntax for the Hora triple itself. I'm using double curly braces instead of single curly braces because the single ones already are used in places like the body of a while loop, and the parser would get confused if I didn't use a different token here. All right, so here's an example of a simple Hora logic rule. And I'll start replacing some of these, I think. Maybe I'll leave the semantics of skip up while I write the Hora logic rule for it right next to it. So here's a nice simple rule. This rule says the program skip is correct according to any precondition as long as the postcondition you ask for is the same as the precondition. In other words, since skip doesn't do anything to change the state, anything that was true before it runs is also true afterward. And you can't go wrong running skip because it doesn't do anything, so we don't have any constraints on what is this thing that might be true beforehand. If you plug this into that definition, you'll see it kind of reduces to a very trivial statement, which has very little to say about the details of the semantics. Does that make sense? All right, so that's our gentle introduction to the rules of Hora logic. Let's try something more complicated. I'll gradually work my way down this board, I think. Erasing the operational semantics rules we've translated into Hora logic rules. So we know how to do skip. Let's look at variable assignment. There are a variety of options for the variable assignment rule. I'm going to follow one particular one, which is longer than the most standard rule that you'll see, but somehow more friendly for the kinds of proof automation that are traditionally done. So let's look at variable assignment. For this one also, I'll take an arbitrary precondition. Assignment is sort of harmless as we've written it, and it's not going to cause anything catastrophic to happen, so we can make it work under any conditions. So I have some arbitrary assignment, the value of some expression e into a variable x, and I'm going to write the postcondition using the explicit lambda to indicate that the postcondition is a predicate over the machine state. So this predicate will consider the variable assignment and the memory. Here's where it gets a little complicated. I'm going to say there exists some variable assignment. Conceptually, this variable assignment that exists is the one that was true here at the time of the precondition. The assignment has, this command has changed the assignment into sigma. Before the command ran, the assignment was sigma prime. And we know our precondition held before the assignment, so it held with the old variable assignment and the current memory, because this command doesn't change memory, so that part stayed the same. And finally, the new assignment equals the old one, where we've properly overridden the value of x. And I'm going to kind of abbreviate this just so I fit in one line here. Blah, blah, blah. All right. So this is another rule. So what it's saying is, if you had some predicate that was true before an assignment, afterwards, you know that you came from a state where that predicate was true, and the change that was made to get to the current state from there is to overwrite in the variable assignment the value of the variable x in the expected way. So this is really, this formula here is more or less copied off of the operational semantics, and you can do that for a lot of straight line commands. Yeah? Yeah, this is an and symbol. All right. Yes?
So classically, that rule is presented with by doing the substitution in the precondition with the postcondition sort of barely there as Q.
Right.
What's the motivation for doing it this way?
I find, so for purposes of automating proofs, you generally want to reason in one direction, either from the precondition to figuring out the right postcondition, or the other way around. And you want all the rules to be oriented in the same way so that your automation fits together coherently. And I personally find it easier to think in the forward direction, so that's why I prefer this rule. All right. Let's see. So the rule for sequencing, or the semicolon operator, is going to turn out to be even simpler. So let me show you that next. We've now tamed the assignment, so I can remove the operational semantics. And the rule for sequencing is going to look a lot like the operational semantics rule. If I know that given P, I can run C1 and arrive at Q, and given Q, I can run C2 and arrive at R, then given P, I can run both commands and arrive at R. So this is one of those cases where there's sort of nothing else you could write. This is the most natural thing to put down. The behavior of sequencing is just to make one thing happen after another, and we see that in each of these two cases here. All right, so now let's take a look at a good rule for the while loop. This one gets a little more complicated, and here's where we see why I included an invariant in the syntax for a while loop. When I write this rule here, I'm just going to assume we magically choose a good invariant. And in the course of writing this rule, I'll sort of explain what is a loop invariant. Formally, what requirements do we have on it? So let's say we picked some predicate I, which we'll call the loop invariant, and let's make that the precondition. And then we have a loop with some test expression and some command. And the postcondition that we deduce here is going to be we exit in a state where the loop invariant holds and the loop test expression in that state has some particular value. What value should that be? When we exit the loop, what's true of the test expression? It's false, right? So that I'm not done writing this rule yet, but let's make sure this part of it makes sense. Whenever we get at the meaning of the invariant is going to be that it always holds at the start of every loop iteration. And when we finally get out of the loop, we know the invariant holds before this iteration. And we know that since we exited the loop, the test expression must have evaluated to false. So therefore, at the point where we exit, we have both the invariant and the fact that the test expression is false. And then we need one more premise up here. I'll kind of separate it from this part. That's not melding into this rule. That premise is going to need to say something about C. And that is going to be, well, here's a good precondition for C. We're going to assume that the invariant holds. So again, the invariant should hold before every loop iteration. So it certainly holds before we get into C. And then we say something about the value of the test expression in that case. What do we think it should be here? Yeah, in this case, when we actually run the body of the loop, the test expression must have just succeeded. So it has to be true. So this is what we assume going into C. And then what C needs to establish is that the invariant is true again afterwards. So the loop is going to run for some number of iterations, 0 or greater. We know the invariant holds at the beginning. Then we're going to run some number of iterations through this loop. This premise tells us that every iteration preserves the truth of the invariant. Finally, the test expression will evaluate to false, and we'll exit this expression, at which point the postcondition holds because we've preserved the invariant throughout all the executions. And by the way, we now know that the test expression is false. So this is one of the key rules of Hora Logic, and it's kind of the essence of how we do implicit proofs by induction. We build the induction into this rule, and the invariant is your clever choice of induction hypothesis. Generally, you pick an invariant manually for every loop in a program, and most of the rest of the reasoning can be automated. Yeah?
So I understand you have one premise there?
One premise.
And then underneath is
Right. Any questions about this rule? Okay. There's one other rule, which is an important one, which we'll be using implicitly in the automated proofs that are going to follow. And that has to do with the fact that rules like these are prescribing very specific forms for the preconditions and the postconditions. For instance, the while rule says that the only kind of postcondition you can prove for while is one that looks exactly like this. You have the conjunction of some invariant and a fact about the loop test expression. You might want to use a different, nicer looking statement of the postcondition that somehow rearranges this, maybe even forgets some information that you won't need as you proceed to verifying the rest of the program. So here's a rule called the rule of consequence. I'll write that in a moment. That lets us take a Hora triple that we've proved and then derive another one in a kind of black box way that doesn't depend on the way that the proof worked. So this is the rule of consequence. So we've already proved some Hora triple, PCQ, and then we'd like to replace it with another one that in some sense is telling us less information, but might somehow be simpler, easier to understand, or allow us to consider fewer cases somehow in another part of the proof. So we can take the precondition we proved before, and we can replace it with another one that implies the precondition we started with. This is called weakening the precondition. I'll write that here. We're weakening the precondition. And we're strengthening the postcondition. So we're allowed to pick a new precondition that somehow may be more specific than the original precondition. Is that right? No, less specific than the original precondition. And the other way around for the postcondition, we can pick a sort of vaguer postcondition, forget some of the things we know are true, and only record a smaller set of facts that turn out to be enough to let us do the rest of the proof. Yeah? I can't hear you. Yes. But this particular form, historically, is presented like this and called the rule of consequence. I've actually proved it as two different rules in the Coq development, though. All right, so let me just quickly show you that this is not just stuff I'm making up, and all these rules are present in my Coq code. Here's the skip rule we saw. Here's the assignment rule. I defined a tactic that's able to prove these because they're following pretty directly from the operational semantics that we wrote before. There's also a rule for memory write, which is highly symmetrical with the rule for an assignment. Sequencing rule, this is nice and beautiful. You can read this pretty directly, I hope. Running C1 we got from P to Q. Running C2 we got from Q to R. Therefore, running the sequencing we got from P to R. Also have a rule for if, which I won't dwell on here. And a rule for while. Proving it here, there are some extra lemmas before we get to the version I showed, which is which one? I guess I haven't quite proved that exact lemma here. This one is almost the rule I wrote up there, except I allow any precondition and require as a premise that it implies the loop invariant. And then we have this premise of C that looks exactly like the one I wrote on the board. And in case you're curious, most of these rules can be proved very directly by just unfolding the definition of the Hora triple. The while loop, you need to do an induction on the big step derivation that appears in the definition of the Hora triple. Because the while can run an arbitrary number of steps, you need some kind of induction, and it works to do induction on this fact here to prove the while rule. And here indeed is where I've separated out one of the two parts of the rule of consequence, just the strengthening case. If you've proved PCQ and you can show Q implies Q prime, then you may conclude that PCQ prime. And this is very straightforward. It follows just by the rules of propositional logic once we unfold the definition of the Hora triple.
Just with while, so you have the more general rule than the one including for, so is there a reason behind this? Or?
To support the automation that appears. Yes. It's a more general rule because it works better with the automation style that I'm going to use. You can prove it from the original rule using the rule of consequence. Yeah. And it is pretty short even. I think it justifies its name. This is all it does. Any other questions about these rules before we start using them? Okay. So here's where we were. And so next, here I have a bunch of tactics that I'm not going to explain in detail, but here's this one you can see is basically just looking at the form of the command and picking the right rule to apply based on what the command looks like. And there are two cases for while, depending on whether the particularly easy form is sufficient or not. And then there's another fancier step tactic that tries the simple one, and if it doesn't work, it strengthens the postcondition and then applies the simpler one. And then a loop here that combines using that with all sorts of simplification of the goal, which I will not present in detail. And now we want to verify some programs. So here's our first example program where you can see the syntax extensions that I mentioned in action. Let's first just look at the program. So this is a program for swapping the values stored in two variables. And those variables are x and y. I have to write the variable names inside double quotes to play nicely with Cox's lexer. Otherwise, I hope you agree this is a pretty plausible syntax for a standalone implementation of this language. So what this means is let's write the value of variable x into the temporary variable, then write the value of y into x, and then write that temporary value into y. So this should swap the values in the two variables. And the way we formalize that requirement in our theorem is that we quantify universally over two values a and b. And we say that, so here's our precondition. It's written as a function over the variable assignment, which I'm writing as s here. And s is a function from a string variable name into the current value of that variable. So when we apply s to the string x, we're looking up the value of variable x, and we say x equals a, one of our two quantified variables. And furthermore, the current value of y is b. And down here in the postcondition, describing what should hold afterward, I've just swapped the positions of a and b. So now x holds b, and y holds a. Does this program and specification make sense? Yeah?
So every variable is in scope all the time?
Every variable is in scope all the time, yeah. So really these are, you could say these are global variables. We don't have any kind of functions or scoping here. Any other questions? All right, so the proof of this one is not terribly surprising. It really follows directly from the basic rules of Hora logic, so I have this tactic called correct that's going to repeatedly pick the right rule of Hora logic to apply, and this one worked, but my Cox system has gotten confused, and someone told me to do this. Okay, I fixed it. And now it's proved. So you could use a tool like Daphne to do a similar proof in a freestanding way outside of Proof Assistant. In the end, the tool would say, yes, good program, congratulations. And you might wonder whether the tool is mistaken. In this case, we can read this theorem statement and sort of expand out all the definitions used in it. And we know that in the end, some Coq proof term in the underlying type theory is being produced that shows that this program really meets this specification. We're not trusting anything about the way that this correct tactic works to believe that we will only accept programs that are actually conformant to their specifications. Right, so that's our first gentle example. Any questions before I move on to an only slightly more complicated example? All right, so I have strategically proved two lemmas here about the behavior of the maximum operator on natural numbers. In particular, if A is less than B, then the max of A and B is B. And I proved that using another library lemma. And we have the other case too. If A is greater than equal to B, then the max of A and B is A. So I proved both of these, and I registered them as rewrite hints, where I say that the right way to discharge their side conditions is to use omega, a procedure that is complete for linear arithmetic. So everywhere in the goals that will be generated for the program that I'm about to show you, we will look for maxes where we can prove one of the two comparisons between the arguments. And if we can, then we replace that max with the argument that is therefore the right answer. So here's our simple program that is going to compute the maximum of two numbers. Like before, we say that in the precondition, variable x stores the value a, and variable y stores the value b. And in the code, we check if x is less than y. And if so, we assign the result, which will go in variable m with y. Otherwise, we put x into the result m. And the postcondition says m stores the maximum of a and b. So an important thing to notice here, it's one of these subtle points with many levels of meta in programming languages proofs. We're using a functional program max to specify an imperative program max. So we're sort of proving an equivalence between two versions of the same program in different languages. But that perspective is implicit in the way I've written this specification. I believe in this case, because I put those two rewrite rules in there, actually, let me temporarily comment this out so we can see what happens. If I say, let's apply the rules of Hora Logic to this one, we wind up with two sub-goals. One where we know that the value of variable x is less than the value of variable y. There's a somewhat unfortunate choice of variable name here of x without quotes for the current variable environment. That was one of the tactics picked that name for us. And we know that the current value of y is the max of the values of, we have to show that the current value of y is the max of the values of x and y, which follows from the fact that x is less than y. And if we use that rewrite rule, then it would be established. And this other case is symmetrical, where we would have x is greater than or equal to y, and we need to prove that x is the proper maximum. So if I go back and add those rewrite rules in here, then the proof goes through automatically. Yeah, that's an artifact of the extensible parsing that I'm not quite satisfied with how it works now. It really means nothing in conventional mathematical syntax. It's just it's like an anti-quote back out of program syntax into regular math syntax. Yeah.
So correct calls omega somewhere? Is that
It does, yeah. I forget if it does explicitly, but we wrote this rewrite rule to explicitly ask for omega, so this will definitely be using omega. When the rewrite rules apply, we use omega to discharge the side conditions. Yeah. Max underscore is covers both cases, and I've just factored it out into two separate lemmas to work more effectively as rewrite rules. No, that's from the Coq standard library. So this It says basically it's the disjunction of the two cases I've considered instead of just doing one case as an implication. All right, any more questions about this simple proof? All right, so let's get a little more ambitious and once again meet the statutory requirement about functional programming and do something with factorial. So here's a function whose precondition says the starting value of variable n is this logical variable n. And we're going to compute factorial in an iterative way with a loop. We're going to set an accumulator equal to 1, then we loop as long as n is positive. We multiply n into the accumulator, and we also subtract 1 from n. And by the end, we should have it be true that the accumulator holds the factorial of the original n value. So note that I've filled in a loop invariant here, but it's obviously the wrong one. I said that the invariant is just true, which is an easy invariant to prove, but it happens not to establish the property we need in the end for the postcondition. So if we're going to verify this program, a good first step is to decide on an appropriate loop invariant. So this needs to be a property that is true at the beginning of every loop iteration and that implies the postcondition when we finally exit the loop. So what would be a good choice of a loop invariant here? Like that? Do you mean switch the order of the arguments to equality? Probably not. And any other ideas? Like that? I don't know. Yes? S of n times the factorial of s of n, sorry, you said accumulator times factorial of s of n should be factorial of s of n. Of n on the right, got it. Okay, and I forgot it. What do we think? Is this a plausible loop invariant? Is it true at the start of every loop iteration? And does it imply the postcondition? We'll be able to ask Coq to help us figure this out soon enough, but it's worth pausing a moment first, because sometimes the goals that come out aren't the easiest thing to reverse engineer to figure out what you might have gotten wrong in the loop invariant. I'm sensing general satisfaction with this loop invariant, so let's give it a try. Okay, correct. What do you think? Yeah, so again, ignore these percent resets. Pretend those aren't there. They're artifacts of the extensible syntax that I would like to make nicer in some future version of this. So what we have here is, let's see, take all these places where you see x0 applied to a string and sort of pretend that the x0 isn't there and the quotes aren't there, and you'll get a more conventional version of this that inflates program variables and logical variables. So we have where we need to prove the accumulator times n times the factorial of n minus 1 equals the accumulator times the factorial of n. Does this look like a true statement? I should also point out we know that n is positive at this point. That came from the loop test here, which succeeded. This is a condition that comes from going once around the loop and trying to show that the loop invariant is preserved. Is this true? And if it's true, is there a succinct way of explaining why? as long as we know n is positive, that's a true statement. So let's prove a lemma that establishes that. It didn't work to apply the definition of factorial directly because we've written this using minus instead of plus, essentially. The definition is +1 oriented, and this is -1 oriented. But we can make that work. I'll say something like this. If we have the factorial of n that is equal to n times the factorial of n minus 1, as long as n is greater than 0, and this is pretty easy to do by case analysis on n. Is this going to be good? Yeah. All right. So let's check that we can apply this rule down here manually, and then we can make it more automated. Let's rewrite with fact s, and I'll write by omega to get omega to prove the side condition for us. So then this factorial should be replaced with something that looks like we have up there. Oops. Why ever not? Oh, I must have picked the wrong one. -1, -1. That's too bad. So I'll say at 2 to say rewrite it in the second place. That could be a candidate. Doesn't like that one either. So I have to confess I only tried the automated proof ahead of time, so maybe I'll just have to switch to that in the first place. But actually one way to do this would be to say 0n here and specify the argument. And now it got replaced, and I'm going to write by omega to make the side condition get proved by omega. So now we're almost there. You can see that the only difference between these, besides all these distracting resets, is that we have to apply associativity of times to get this to work, and ring would do that for us. Okay, but to avoid these horribly long 2 lines of proof, let's add a hint up here. Let's say rewrite hint, and you should discharge the side condition using omega. So now we should see just one proof obligation left. Okay, good. So here's this one. Is this one true? Hint, yes. And well, what lemma could we prove to show that it's true? I agree. Okay, so n is less than or equal to 0, and we're in natural number land, so it must be 0. That's a good first step. So that's a good 3-step process. Let's prove that factorial of n is 1 when n equals 0, and then the other automation will piece together the other steps of your argument. So we'll say if n equals 0, then the factorial of n equals 1. All right. So now we can write to the Millennium Foundation and collect our $1 million for solving this challenge problem. You're asking about a step in the more manual proof and how it worked?
No, I wanted to look at the goal again.
Which goal?
The formula.
Okay. Yeah, so H0 I think is the Loop Invariant. It was already used to rewrite the conclusion automatically by the correct tactic, so we can sort of ignore that for now. So let's put this back. Okay. Any other questions about this example? Yeah.
So if you, is there a way to show, or maybe this is showing that, like that it's not writing to a variable b, for example?
Yeah, why not? Let's do that. So at the beginning, B was B. And by the way, right now, B is B. And it also happens that here, B is B.
Okay, so if you, for each, there's no way to say for all variables that are global. Like if you have a bunch of global variables, like let's say you have 100 global variables, so, and you want to say that none of them are top, would you manually map all of them?
We could do that here. We could write for all x such that x is not equal to n, and x is not equal to ac. Then s of x equals values of x. Now I'm curious if this is going to go through automatically, so let's see. Oops. Loop. Loop. Yeah, I have some surgery left to do. Some things subtly have appeared at the end. Okay. Yeah. But you can see this would get tedious to write for longer programs. But you can introduce a notation where you explicitly list the variables that aren't going to change, and you can even build that into the Hora triple or something if you really wanted to. But there are potentially some problems scaling this up to larger programs. So a problem with this spec, maybe you're saying this, is that it sort of leaks implementation details. If we used an extra temporary variable, we'd have to change the spec, and that would be sad. We could kind of make up a convention for variable names that indicate they're temporary or local, and only say the others don't change, something like that. Oh yeah, let's do that. Important gets important plus 1. Important gets important minus 1. Oh, too bad. Probably this is true, but let's not bother with it. In theory, that should be possible to make work. All right, any more questions about this proof? All right, let's go to the last example that I have queued up here, which is selection sort. And I have proved this lemma boring and useful for the particular proof that I found before. If two numbers are equal, then the results of some function applied to them are less than or equal. Just happens to be a good hint for eauto to use in a particular case that I came up with before. And I'm registering using this syntax. I won't explain entirely that omega is a good thing to try in various circumstances where you're testing natural numbers for equality. So given that, this is an implementation of selection sort. And the basic way it works is, well, let me give you the spec first. So this is a function that actually uses the memory. We're going to do in-place sorting of an array. And this precondition is true. It's going to work for any initial state. And in the final state, we essentially know that some array is sorted. And let me draw you a picture of what this means. This is going to be a representation of the postcondition there. So here's the memory. It's a big old array of values. Actually, it's infinite in this case, but I'll draw it as finite. And here's an array. I'll call its contents capital A. And the local variable A points to the beginning of the array, and the local variable N indicates how wide the array is. And that postcondition is basically capturing that convention plus the fact that A is sorted. For the complete correctness condition for sorting, we'd also want to say that the output array is a permutation of the input array. I'm just doing the sortedness condition here to make this a little easier to digest. So this condition down here says for every two indices I and j, where I is less than j and they're both less than n, the size of the array, if we look up the two array cells, they're sorted in the right order. And we do that by using the local variable A as the base of the array, adding the index, and then looking up that cell in the memory, which is coming from this variable m that's bound by this funny notation right here. So we're binding both the memory and the local variable environment here. So this condition says after this code runs, the array is sorted. And the way the algorithm works, in case you've forgotten your basic sorting, which I certainly had when I set out to write this example, we set a variable I equal to 0, and then we do a loop over all values of I from 0 up to n minus 1, where n is the array length. Then we set a variable j equal to I plus 1 and a variable best equal to I. And best is going to be storing, as we go through this loop, we're going to examine all the array cells starting from I up to the ends of the array and find the lowest number, and then that number is going to get moved to the beginning. So we have another loop that does that. I'm using this bracket notation here to indicate a memory read. And so we look up, we check an ordering comparison between cells j and best of the array. And if j is actually even lower than best, then j becomes the new best. And so we do that loop, and then we swap the values found in positions best and I. And those might actually be the same location, by the way, so we have to be a little careful about that. And so every iteration of this loop finds the lowest array element that has not yet had a confirmed place and swaps it into that position, and then continues examining the subset of the array that's after that point. So our primary challenge here is to write some good loop invariants in here that will establish why this is true. This precondition is not a marker for us to fill in. True actually is sufficient for this example. So any questions about the specification of this code as written down here and kind of interpreted in that picture? Yeah?
Can you remind me why you use delete?
It's just a particular syntax I defined. It's a special, think of it as built into the syntax of this embedded programming language. Any ideas what would be a good loop invariant for the outer loop? So the purpose of the outer loop is that variable I tells us a boundary for how far we've gotten in picking elements to put into the right positions at the start. Let me draw a picture I'll do the pictorial version of this loop invariant, or we could try to make it more formal. Loop invariant number 1 says, it looks similar to the postcondition, but it's a little more, there's some extra cases introduced. So here's what we should know at the start of every iteration of the outer loop. We have the same array as before, but now we have I indicating some split of the array into two parts, A and B. And the first part, we've already sorted. And the second part has the property that every element in it is greater than or equal to every element in the first part. So we know that we didn't mess up in an earlier stage and pick the wrong thing to place in a position within A. And as this code runs, we think of, originally the A part here started out empty, and as we run each loop iteration, it grows and grows and grows, and we pick the lucky winner from B at each stage to move into the last position of the new A that we've grown into. That is basically how this works. Does that picture make sense? So how can we translate this into, question?
Do we need that everything in
We could say only that the last element of A is less than or equal to everything in B. I don't know. I haven't tried that. So it might get a little tricky because the A region starts out empty. So we have to make a special case for that. So let me start us off with one part of this invariant. Let's remember that S of I is less than or equal to S of n. And then something else. Which part of that picture is not yet, the picture for the loop invariant is not yet represented here? Yeah, I'm going to use a shortcut here. We already defined sortedness there, but this isn't quite what we want to say. How should I modify this? Yeah?
Just replace S of n with S of I.
Right, so the sortedness has only been enforced so far up to I. So I'll put that there. Okay. And this might be enough for that loop invariant. Except that captures the first of the two conditions that have a comma between them there.
There's no element in B which is less than A equal to B.
Right, we still need to get the part that says A less than or equal to B. Yeah.
Because we import the order in the part of A variant, we could simplify the both condition just to be sure that
I didn't hear the last part.
we can simplify the both condition because when we step we will make sure it's ordered, we just have to make sure that we use the end of the variable. Okay, this is the end.
I don't understand.
If I is n, if I is the array,
Yeah.
we can do all sorted.
That would prove what we want to prove, but we would have to inspect the proof to see that it proves that we want to prove.
I don't think that the post condition is redundant in the
Postcondition is not redundant. Everything between here and here is implementation details that we want to be able to ignore. The postcondition is part of the theorem statement. It's important to write it so that we know what property we're trying to establish. The loop invariants are just part of our proof technique. So in some sense, it's the loop invariants that are redundant with the postcondition, not the other way around. So to get that second part of this invariant, we need to show, let's see, we have two indices. One of them is less than I, and the other one, j, is greater than equal to I. And they have the appropriate ordering. I think that'll do that part. And then,
We want j is less than 10 or something.
oh, good point. Let's write it this way then. Just j is greater than or equal to I and also less than n. Let's just check that parses and everything changed that ahead of time. Yeah, so that works. All right, so let me back up out of that and give us the whole screen again. And let's optimistically copy this down over here. Okay. We need to get a little fancier here in giving the inner loop invariant. What's an example of some additional property we're going to need to remember here? Okay, so let's see. I'll write that as for every k, which is, so we're inspecting starting at I, and we've gotten up to j. It had better be the case that the memory at position best is less than or equal to memory at position, I'll give this a new line, memory at position k. All right. And I'm also going to remember I is less than j, which is less than or equal to n. And we should know something about best. Best is between I and n. All right. Anything else we might need to remember to get this induction to go through? Don't believe what I just wrote. Let's see. Well, it's used in the loop bound here. It's used as the bound for both of these loops. This is probably worth trying. See how this goes. So we have 4 sub-goals left. One of them asks us to show that that cell j of this array is less than or equal to cell k of this array. So this must be, we only use the variable k in one place, so it must have to do with this condition here. We're trying to show that something, I think probably this is the case where we have assigned best from j, and we're trying to show that that new best value really is less than or equal to everything. And at this point, I'm going to use a slightly more manual proof style and do a case analysis here on, let's see, so k is less than or equal, k is greater than or equal to I. It actually matters whether it's k is less than x0 j plus 1. I think what we want to do here is a case on whether k equals j. And this just happens to be a good way to do a case split on whether one natural number equals another or not. So we're going to get 2 cases here, one where k equals j and other where k is not equal to j. In this first case, we see k equals j. And let's see if we can then make progress in those cases. Now there's just one case left. And I think what we need to do is take our hypothesis h and specialize it to the particular value of k that we've chosen here. This is the sort of detail that is best digested after the fact. I'm mostly just trying to show there are just a few steps left beyond what the proof automation does for us. So that one's gone. And then is this one going to be the same reason? I think in the interest of time, I will copy I think about 3 lines left that I had before when I worked this out. I'll just copy this whole deal in here. So we run correct, and then afterwards we find every case where we are writing to a memory location and then reading back. We're writing to one array cell, reading from another. To understand this, it's good to do a case split on whether these are the same array cell or different array cells. So that's all this loop does. It considers every way of considering whether 2 array indices are equal or not. So this will get rid of most of the cases, and then we have exactly the case I just showed you, and one more case which is essentially the same. And I think all this is going to go through, assuming we reconstructed the loop invariant in the same way as when I wrote this before. Okay. So there is verified selection sort. Any further questions about this last example or any of the other lead up to this point? Yeah.
The automation getting noticed being slow. Other, how do you deal with
Patience?
that? But you must have ideas for speeding things up.
Yes, but that's a work in progress. It involves negotiating with the Coq development team. Yeah. Short answer is yes.
We probably also want to know that the resulting array is a permutation of the original array.
Maybe you want to know that. Yeah.
Is there a good way to, like, when you're using your LTAC rules that, like, search for proof and things like that, is there a way to get, like, output that says, I did tactic this, and then I did this, and then I did this, and then I did this?
Ask Clement about that. That's what you were working on, right? Yeah, sorry. He built an Emacs function that helps you do that.
Alright, pattern variant. So we cannot prove or
I hope so. It's an unsound system, but depending on what you mean by bad, it's an unsound system if you can prove everything given a bad invariant. Or we could define bad to mean you can't prove it. And then obviously also you can't prove it if it's a bad invariant. Yeah.
Can you offer any insight as to how well this scales to larger here? I mean, it seems like function sort is typically a very small part of the work program. And I mean, I think it would take me a lot longer to do this. I can imagine sort of using the program. So I'm sort of feeling despair.
The general process scales to pretty large programs. Doing this inside a proof assistant with this style of small trusted code base is a relatively new thing, and there are all sorts of pragmatic issues with performance and so forth that are still being ironed out. But I have suffered through very large proofs of deployed programs with users in this style, and it's possible to do that. I guess that was about a 1,000-line program that took about 6 months of work, and the job got done. Yes, and we can talk about whether there should be any million-line programs, but that's another conversation. Yeah.
Are there any automated ways of finding loop invariants that would sort of help me find?
There are, and you can imagine adapting a number of them to Coq. I don't have any personal experience with that. I'm not sure anyone else has tried implementing that either. But there are abstract interpretation-based approaches to inferring loop invariants. Yeah.
Can you work at all with an extension of the language that has functions?
Yes. You can define all that from first principles too, and it turns out just fine. Okay, thank you.